Okay, in previous video we talked about different types of number, basically their classifications and all, and we got a fair idea about what is real number, what is rational, irrational number, integers and those stuff, right? Now let us try to jump into some more interesting concept in calculus. Before we go to deeper into the calculus, we need to understand their building blocks. Okay, so one of it is function, because without proper understanding of functions, studying calculus will not be possible at all. Okay, so let's see what function is. Now before we jump into the mathematical jargon, let's try to see what function actually meant. Okay, then maybe we will see how mathematically we can express it. Now let's say we have a spherical balloon or something like that, okay, with radius r. Now if somebody says just to calculate its volume, what will be its volume? It will be just like 4/3 pi r cube, right? Now let's say we are taking a bigger balloon over here, okay, with a radius of capital R, where my capital R is greater than my small r, because it's a smaller balloon and it's a bigger balloon. Okay, so that's the difference between these two. So what will be this guy's volume? So this will be 4/3 pi r cube, correct? So now think about this one. When my capital R is greater than small r, that means we are talking about a bigger number over here. The cube of that particular number will be also bigger. That means my r cube will be greater than this small r cube. The capital R cube will be greater than this small r cube over here. So that means as 4/3 and pi are constants, so we can say our capital V will be greater than small v over here. Okay, so what we are trying to achieve it over here, if you see, we can deduct from over here is, if we make this radius bigger and bigger, the volume will be much bigger and bigger as well, right? Because we are dealing with positive numbers over here, positive real numbers over here, right? So that means this radius, this changing of this radius has a direct impact on the volume of this spherical balloon over here, correct? So we can say volume is a function of radius over here, where the volume is actually the dependent one and the radius is actually the independent one. That means if we change radius, the volume will be changing. So how it will be changing? If we take greater radius or bigger radius, the volume will be bigger. If we take a smaller radius than this one, the volume will be smaller as well over here. Okay, so this is nothing but the concept about function over here. We have something which is having an impact on something else over here, and in real life you will see functions everywhere, just like volume and temperature as well over here, right? For liquids, if we increase the temperature, its volume is increasing over there, right? So you will find in real life functions everywhere. That's why studying of functions are really important over here. Okay, so in very simplistic term, we can define function something like a box over here, or some process where we have providing some input, in this case radius, and it provides some output to us, right, which is nothing but the volume in our case. Okay, so this is a intuitive way of seeing a function over here. Now when we'll study calculus, we need to define function in mathematical way as well. Okay, so let us try to see how we can define function formally, and for that, so the formal definition of the function involves the set theory over here. Okay, so this is how we can define it. So we will go by the same example we have seen in the previous slide. Okay, so we have, let's say, this particular set of numbers over here, which is nothing but our set of radius over here. As radius can only be positive, it cannot be negative, so we can safely say it belongs to the R plus. That means the positive real numbers. We talked about this R plus in our previous video over there, right? Similarly, the set of volumes, we can think about as a r plus as well, because volume cannot be negative over there, right? Because as radius is positive and 4/3 and pi both are positive, so volume will be positive as well over here. So we can say this radius and this volume both are belongs to a positive real number set over here. Okay, now let's say these are the and how this radius and volume are connected, these two sets are connected or related to each other is with this particular function, right? With this particular equation over here, volume is 4/3 pi r cube over here, because there could be numerous number of relation between two sets, right? So for this case, these two sets are related by this particular function or particular equation over here. Okay, now let's say we have couple of data points over here for radius set, and similarly for volume some data set. So if I'm just giving you, it could be any numbers over here, the dots, so it does not matter. If we choose any number from here, so let's say this guy over here, any radius, let's say 1, so there we will be finding some volume over here, right? Now think about this one. If we choose a separate number over here, the volume must be different over here, because the cube of two different numbers are always different over here. So that means for this guy, if we choose let's say 1, we will always get a specific volume over here. Similarly for other numbers as well, correct? Okay, so this set of radius, it's also called a pre-image, and this set of volume, which is nothing but the dependent variable over here, which also called the image over here. So as we have seen in previous slide, radius is the independent one and the volume is the dependent one, right? The set of the independent variables is also called the pre-image, and the set of the dependent variable is also called the image over here. Now from this discussion, we are noticing couple of stuff over here. Is each element in the set radius has an image in set volume. That means if you choose any number, any positive real number over here, and if you put it over here, you will get a particular volume over here as well, right? That means each and every number, and it is possible as well, right? We can have a spherical balloon of each and every real number possible in a r plus set over here, right? So that means each and every number has a particular image in the volume set. So that is what we have seen it over here, first thing. The second thing, which is the important one over here, is every element in set radius have one and exactly only one image over here. If you see, as I told you, as two different numbers will never have the same cube value over here, that means for these two guys the volume will also be different over here. Okay, so this is very much important. Each and every element in set radius have only one image over here. Okay, so that means for a particular radius you will never get two different volumes over here, so that will never be a function. That is actually we have a special name for that is called the relation over here. Okay, so that is very important over here. So we will never get two different values when we put some value over here. Okay, now let's move on. Let's talk about more about this formal definition over here before we express it mathematically. Let's say we are taking a very simple example over here. Another example over here, we have two sets A and B. Okay, A set has only these numbers 1 2 3 4. B set has only these numbers over here 0 3 6 8 12 and 15. So these two are related with this particular equation, x square minus 1. Okay, so if you see, if you just put 1 over here, so this is nothing but our independent one and this is the dependent one. If you put 1 over here, we'll get 0. If you put 2 over here, we'll get 3. Similar stuff. Okay, so according to the discussion we have in our previous slide, we can see these two things. Each element in set A has an image in set B. So each and every element in set A must be having an image over here. So that is there. So that is actually the first rule of the function definition. Also, the second rule we learned is each and every element in A have max a single image in B. Okay, one and only one image in B. So that is also, it is satisfying over here. Now, if you see it over here in the set B, there are two elements 6 and 12 which do not have any pre-image over here. Okay, so this is also possible. The dependent set can have some elements. It's possible that a few elements in the set B, which is nothing but the dependent set over here, are present which are not the images of any element in set A. Okay, it is possible. The main rule is that all of the elements of set A must be having an image over here, and that too a single image over here, one and only one image over here. There could be some element in the dependent set B which may not have any image over here. That is possible. Okay, so this was the missing part of the function definition, so that we completed over here. Okay, so if I just see the mathematical notation now, so we have two different sets, x and y, and they are related with the function fx. In our case, we talked about the volume 4/3 pi r cube, also x square minus 1, right? Both are functions, and we can express the function in something like this one: f, then colon, the set, basically the independent set, then this right arrow, then the dependent set over here. So you can also express function in this way as well. Okay, and if you see, like, the formal definition of the function is already involving the set theory over here as well. So that means we can write something like y, which is basically nothing but an element of this particular set. Y is nothing but the f of x, where x belongs to this set x, which is nothing but our independent set, and y belongs to this set y, which is nothing but our dependent set over here. Okay, so this particular definition of set theory also allows us to write the function as a set of ordered pairs. Okay, so that means if we just go back to our second example, x square minus 1, we can express this function f over here something like a pair of elements over here, where the first element is coming from the set A, which is our independent one. The second element is coming from the set B, which is our dependent one. That's why 1, 0, 2, 3, 3, 8, 4, 15 are the parts of this function over here. So we can write this whole function as a set over here, set of elements, where each and every element is another tuple over here, right? And for that tuple, the first element is coming from the set A, and the second element is coming from the right hand side, which is the dependent set over here. Okay, so we can write something like the function f, which is a function between set A and to the set B, can be considered as a set of ordered pairs. A is coming from the set A, and B, which is nothing but, we can also write f of A. Okay, because as B is f of A over here, we have seen in the previous slide, which is belongs to B over here. Okay, so we can easily say that f a function is a subset of A cross product B, right? So if I just take the cross product of A and B, it is nothing but 1, 0, 1, 3, 1, 6, 1, 8, all these things, right? Then 2, 0, 2, 3. Then f must be a subset of A and B, A cross B over here, correct? So we can also write functions in this way as well. Okay. Now let us take a couple of examples and analyze what we can call it as a function and what we cannot call it as a function. The first example we'll take is, let's suppose we have a function from R plus, that means the positive real numbers to any real numbers. It could be negative as well. Okay, where the function is something like this one, y square equals to x over here. Now, one thing to notice over here is y square equals to x. Now, in previous all the slides, whatever we have seen, we have always seen y equals to f of x. We never seen y power to something, right? So that's why we need to express it in our term over here, right? So y square equals to x, we can write something like y equals to plus minus root over x. That we can do it, right? So now this particular form is actually matching with the form we know about function y equals to f of x over here. Now if we just plot this guy over here, one interesting thing is coming up over here. If you see y equals to plus minus f root over x, right? So this is the curve for plus root over x, and this is the curve for minus root over x over here. Now let's say we have a point over here for a particular x value. If we just plot it over here and try to get the y value over here, we will get two values over here, right? One value will be belongs to this plus root over x. The second value will be coming from the minus root over x over here. Okay, so that means this is an interesting one. If we just draw the similar set diagram we have seen before when we define the function formally. So let's say we choose the value of x equals to 4. So what are the value I will get over here? Y equals to plus 2 as well as y equals to minus 2. Similarly, for x equals to 9, we will get two different values over here, plus 3 and minus 3. Now think about the function definition. When we talked about definition of the function, we said this guy, the pre-image over here must be having one and only image over here. But if you see, if we just put the x over here, we are getting two different values over here. So this is violating the second clause of the function definition over here. So that's why we cannot call this guy as a function. As I said, this has a very specific name called relation. Okay, so relation we can think about as like a very generalized case of functions. So functions we can define basically from the relation only. We'll see in the final slide. So let's take another example over here. So let's say we have a function from real value set to real value set where y equals to x cube. So this form we already have it in our form only, y equals to f of x over here, right? And if we can plot it over here, so the curve will be something like this one. And if you see, like, there is no way this curve, the two portion of the curve are actually, we will never get two values when we take some x over here, correct? So let's say we are taking x something like 1, 2, 3, 4. The value of y will be 1, 8, 9 and 64, right? So each and every pre-image has one and only image over here, correct? So that means we can safely say this guy is a function over here. And if you see, like, all the elements over here has an image over here as well. Okay, so we can safely say y equals to x cube is a function over here. Okay, so hopefully these two examples makes clear what we can call it as a function and what we can call it as a relation over here. We cannot call it as a function over here. Okay, so if we just take the summary from whatever we have learned so far, so we can make a statement like the function f from set A to B is actually a relation which is basically satisfying the following properties. So f must be subset of A cross B, which we have seen it. For all A belongs to A, that means this is our left hand portion of the set, that means this is our independent set over here. We will be getting a tuple over here, A comma f of A, which must be belongs to f over here. Okay, now the third point is very much interesting and important over here. Let's say we have A comma B which is belongs to f, okay, and A comma C which is belongs to f, then B must be equals to C, because as we have seen, if we have entered a specific value to this function, we must be getting a single value, unique value over here. That means each and every pre-image must be having a one and only image over here. It cannot have two different images over here. That means if A comma B belongs to f and A comma C belongs to f as well, as both of these pre-images are A, then B and C must be equal over here. Otherwise we cannot say it is a function over here. Okay, so hopefully we got a fair idea about what function is. From the next video onwards, we'll talk about more interesting stuff over here. Okay, so hopefully this video was helpful. See you in next video.